Okay, now we're going to be talking about operators on vector spaces, and there are some important operators, some basic but important operators on vector spaces. There's the identity operator, the inverse operator, the adjoint operator, and the projection operator. So the identity operator is something that takes something from the input space, maps it to the output space, where the output space is actually the input space. It's the same space between the two. Okay, and every point in the input space gets mapped into the same point in the output space. Okay, so another way of drawing it is like this. Every point gets mapped back onto itself. Okay, every point in the entire space. So that's the identity operator. It basically takes a point in the input space, maps it back into itself. So that's a fairly simple one. The inverse operator of an operator. So inverse of operator G is given this way. So I have some operator G that takes X, maps it into Y. The inverse operator takes the value Y and maps it back into X. And that's true for every element in the input and the output space. So in order for this kind of thing to happen, the input and output spaces must be closely related. For example, they must be identical. They don't have to be identical, but there's too much going on here for this to make sense. Every point in this space has to map into this space. Every point in here needs to map into there. Okay, so G maps from the input space to the output space. G inverse maps back, and it happens exactly. So whenever this happens, it's called a bijective map. Okay, it is one-to-one and onto. So that is X maps onto one point, and this, or rather, this maps into the entire space, and this maps back into a single point. Okay, so that's the inverse operator. The adjoint operator is a little more complicated. Okay, the adjoint operator. So here I have an input space. I map through G into the output space. The adjoint operator maps back from the output space to the input space, but not necessarily bijectively like the inverse. In other words, these two spaces could be radically different. So unlike the inverse operator, which basically required these to be very similar to one another, the adjoint operator does not require them to be similar to one another. So how is the function G defined then? It's defined by an inner product. Okay, you need to have an inner product in order to define the adjoint operator. So here's how it's defined. So remember, you have an input space, you have an output space. So X is in the input space, Y is in the output space. So since G maps from input to output, then G times X is in the output space. And so here I have an inner product on the output space between Y and G times X, where G is something operated on from the input space. So I have, this is a quantity, this is an inner product on the output space. I also have this quantity on the input space. X is in the input space. When I take something from here and map it through G adjoint, I get something in the input space. I'm taking an inner product then on the input space. And so the adjoint is defined so that these two inner products are equal to each other. So this kind of a definition is called an implicit definition. This doesn't tell us exactly what G adjoint is, and in fact there may be an infinite number of G adjoints that do this. There may be. But this is the definition for the adjoint. Okay, adjoint operator. So again, the adjoint operator is always defined even if the input and output spaces are radically different, whereas the inverse operator pretty much requires that the input and output spaces be the same. Okay, so that's a big difference. And so again, the definition is based on the inner product. And so we'll come back, and when we look at the example problems, we'll look at some pretty complicated ones, and we'll see how all of that works. Okay, how it comes out. So again, here's the definition for the adjoint operator. This definition is implicit, based on the inner product. the input and output spaces have their own norms defined, the operator G is assumed to be bounded. So here, again, I'm talking about general operators. I'm not necessarily talking about matrices, although matrices are definitely a linear operator, can be used as a linear operator. The adjoint operator is defined even on, for example, functions that are continuous on the space from 0 to... They're defined on all kinds of math operations, not necessarily just matrix operations. Okay, so here we're talking about the adjoint of an operator. Here are properties of adjoint operators. If the operator is identity, so the identity operator satisfies this. The adjoint of the identity is equal to the identity. Okay, the adjoint operator of the identity is equal to the identity. So when we have an identity, that means the input and the output spaces are the same. And so anyway, we get this. So in this case, it actually shows that the identity operator is also the inverse operator, which is kind of interesting. If the operators F and G operate on the same spaces, then F plus G adjoint is equal to F adjoint plus G adjoint. So what is this actually saying? I have two operators, two linear operators. I'm taking the adjoint of that sum. I can show that that's the result that I get is the same as operating on with one adjoint, then operating on the second adjoint, and then adding the results. Okay, so these are not matrices; these are operators. Okay, so it's kind of complicated to think about what this means in general. If alpha is a scalar, then we have this relationship, a real scalar. If it's a complex scalar, then you'll actually get the conjugate going here. If the operations make sense, F and G. So what does this mean? This means that first you have some input that's getting operated on by G. The result of that gets operated on by F. Okay, that's what this is saying. This equation is saying that this concatenation of operations, the adjoint of that is equal to the concatenation in the opposite order of the adjoints. Similarly, if the inverse exists, F inverse adjoint is equal to F adjoint inverse. And so you can prove all of these based on the definitions of the adjoint operator and, for example, inverse operator and so forth. Okay, so that is an important thing. So I'm going to give you some examples in the practice problems, but just to kind of give you a taste of what's going on here, we'll consider the adjoint operator of a real matrix. So here G is an m by n matrix. Okay, so our operator G is an m by n matrix. Our input spaces are n, output spaces are m. We can go through and show that the adjoint operator is actually A transpose. So, and if A is complex, then the adjoint operator is the transposed conjugate, or what is referred to as the Hermitian transpose. So if you have a matrix defined in MATLAB, A with an apostrophe gives the adjoint of A. So this is the adjoint operator. So some important things going on there. All right, projection operator. This takes something from a vector space, maps back into that same vector space. So again, the input and output spaces are the same. So the projection operator is an operator that satisfies what is called the idempotent property. The idempotent property is this. I have E that operates on some X in the vector space. Okay, that is going to give me something back in the vector space, which I can then operate again. So I operate again. I do an operation on the thing, and I operate again. And so I can actually write it this way, E squared, which basically means this. And this is the result. That E, when I operate on X, the quantity that I get, if I operate on E again, I just get the same as E operated on X. So that is, when I operate on this, I get itself back. So repeated operations on using E act just like E. Okay, so that is what a projection operator does. I can keep operating, doing the same thing over and over again, and I get the same result. So an example of a projection operator is the identity operator. So remember, it maps x onto itself. So the identity operator, I get x. If I do it again, I still get x. And I can keep doing it as many times as I want, and I still get x. So for any subspace M of V, there exists a projection operator that will map V onto M. So this is an important thing. We're going to see how to do some of this depending on the subspace that we have available for us and how we have it defined. But we can actually, given a subspace, we can actually find a projection operator that will do this map. If E is self-adjoint, okay, that is, it is its own adjoint. That's what this means. E is equal to E adjoint. That means E is what is called self-adjoint. So if a projection is self-adjoint, it is called a projector. And that's a very powerful tool, is working with projectors. So basically, I can think of it this way. I start with my input space. My projection maps into my input space. And notice when it projects from this initial input space over here, this y is not necessarily the same as x. This y could be different than x. But if I operate on this point again, I'll get y. I'll keep getting the same value. Okay, so that is what a projection operator does. So these are important operators for vector space.